Hi, this is Paul Gregg, and I wanted to make a video about one of the people I've helped around the world to build a backyard roller coaster. I actually just design and analyze it for him. I've helped quite a few people. People have bought our 2 ebooks and then contacted me, and I've been able to help out a little bit. One that turned out really good was Scott Brazelton and his backyard roller coaster shown here. In 2017, he had bought our 2 books, was going to build one, and stopped by our house. He's a Navy fighter pilot stationed about 2 hours north of Seattle, and he came by and looked at our small backyard roller coaster. He has a 3-year-old son, and he was excited about building one, and I helped him out a little bit on the design and analysis, and I got his permission to talk about that. The first thing you do for a good engineering project is write down your design requirements and objectives. And he intended this for a 3 to 6 year old, his son, 35 to 50 pounds. Maintain a factor of safety of 1.5, low accelerations, fairly low speed, 10 miles an hour. A small cart, 8 wheels on the cart. I've been experimenting with 4, but I've decided 8's a much good number. He had a large area, wasn't constrained by any space. It was fairly flat. He wanted to put all the safety features that I recommend in it, and have an adult-powered lift, so there's no motor or chain or the expense and risk of something like that. He said he'd like to build something like my little rocket roller coaster and make it a little bigger and a little more interesting and maybe a little faster. So I had, here's a picture of my little rocket. I've been documenting a lot of track layouts in this method, and these are the simple ones. But I had made a backyard roller coaster 3DO2, my smog one, if you know about that. 8.5 feet tall at the lift hill, 170 feet long, and I call it over, under, over, under. The lift hill goes up over the track, and then dives, picks up a lot of speed, very thrilling, goes under the track, gains a little bit of altitude here back, and does a great big swoop around to the right. Goes fairly slow at the overpass there, and then goes through the trees underneath. This is what it looks like. There's the lift hill, 8.5 feet high. Picks up a lot of speed, going way down, big dip. Comes up, loses speed, starts this big bank turn over there. It goes fairly slow right there. Goes through the trees, goes under the lift hill, turns to the right, and goes back to the start. And I had the idea that the really nice track for small kids that wouldn't be too big would go up a lift hill over the track, not under, and it would just start from maybe do a small dip here, go back up, and from here just do great big right bank turn, left bank turn, right bank turn, really fast, big banks right back to the front. I call that over, over, under, under. A little less scary than the big dip one, but fast, fairly fast overall, and maybe scale it down a little bit. And so here's a layout that Scott sent, and basically what I need for my simple analysis, relatively simple to professional analysis, is I need the heights. I need some stations, some points in space. Here we chose 17 of them, and basically this is the lift hill, goes through a moderate dip back up to a peak, a second peak, and then starts a gradual descent through large bank turns, goes real low here and just does a lot of bank turns till the energy runs out at the end. So the way I do this is through a spreadsheet. I have other videos that go into detail on this, but I'm going to go through this fairly quickly. Basically, these are all the points in space. The lift hill peak, the dip, the next hill, and then just a gradual descent, picking up speed. I use meters and then feet. These are the potential energy calculated from that. And then there's a drag coefficient that I kind of simplify just based on the length of track it's gone, and I've calibrated that to testing, and it comes out pretty good. The joules that are lost to drag energy, the energy that's left over, that's once you know those number of joules, it's easy to calculate by a simple formula. The velocity it'll be going, and as you can see, the velocity starts out fairly high, slows down at that second hill, and then is fairly good, 8 to 10 miles an hour through the big bank turns all the way to the end where it's going 4 miles an hour. And a total time 15 seconds in the end. And from the videos, I've found that it really does take about 15 seconds, so I feel good about that. The nice thing about a spreadsheet this way, with these simple calculations in it, is that if you didn't like something at the end, you could just change something up the front end and all the calculations just blast out with one click. So if for instance, if I thought 4 miles an hour was too slow at the end, I could make the initial lift hill a little bit higher, just change that number and then see what happens down here. And if I wanted more speed in a turn, I could change a radius, or I could change, if I wanted more G's, I could change the dip radius, and I could do that. Now this is the same spreadsheet just to the right of it, so it keeps going. These calculates the up and down G's. You can see at the first dip it goes, including gravity, 1 G for gravity, 1.85 G's. That's fairly nice for a little kid. And then it gets him a little bit of not air time, but a little bit of a feeling of weightlessness at the second hill. And then, so that'll be nice, but not too severe. The last part of this is calculating the sideways G's, and then from the turn radius and the velocity, there's a formula for calculating the optimum bank angle, and that's what's here. So you can see, once we go through the straight part, we start the right bank and the left bank, we get up 40, 45 degrees bank angle, which is really nice, you know. That's the optimum bank angle for a person feeling like they're just being thrust into the seat and not leaning left or right. So that looked really nice. I usually subtract 5 degrees from the optimal bank angle so that the inside side wheels are always engaged to the track, and that makes the ride a little smoother, so the kart is not always hunting for the track back and forth. Makes it a little more efficient too. This is my attempt at 3D modeling the track in Fusion 360. Turned out fair, but I'm not satisfied with it. Basically, at these different stations, I just put an angled bar in, ran a ribbon through those surface, and then put some rails on the outside of the surface. It worked fairly well, except where the ribbon connects at the end. This is not satisfied with this, but basically you get to that point and you're just going to build anyway. So you know what height and what length. He used my method for hot sand forming of the PVC conduit 2-inch pipes, schedule 40, because it's a little kid. And I think he spent about $1,000 on the all of the materials, kart and track. So this is really the fun part about building a backyard roller coaster, is when you get to this point, you've formed your rails, you've painted them to protect them from ultraviolet radiation from the sun, and then you start making some frames and putting it, sending the track off into space and putting up on chairs and ladders and stuff, and start to build in the frames. is really the exciting part about it, because it really starts to come together. And so the way you do this is you build some frames where you know the height is a certain place, start putting it up there, and then just run it in the air, keep connecting the pipes, and temporarily prop it up, build in frames to fit. And then there's a spine that goes on here, a third, the two rails, and then a 2x4 spine that makes a nice stiff truss structure that he's going to put on here. And then you put diagonals between the frames, which really stiffens things up. This is stiff and strong. When an adult can easily walk over the top of this, and it's very stable. A lot of people who build backyard roller coasters like to put 4x4 posts in the ground and big chunks of cement, piers. I don't like to do that because I don't want it to be that permanent. And actually, this is a cheaper way to do it because 2x4s are so inexpensive, at least in the U.S. And PVC is inexpensive, at least in the United States. So, this is looking at his aft end. He followed my designs fairly well, and then did some things a little differently, and I'll talk about them. His rider is really pretty small, so he doesn't have to worry about being too good on the engineering, but he tested it, and so we know it's good. He went around the track twice with 100 pounds, everything held together, nothing bent or cracked or anything like that, and so he feels pretty good about sending his 50-pound child around there after it's been run around with 100 pounds of sand in it. He did a great job on theming. He, like I'd done for the little rocket, he got a 15-gallon water barrel and cut the side out, and did a great job putting PVC pipes in for these little pistons on his engine, and put a wood propeller on it and some tail and wings and stuff. Looked great. His little boy was really happy about it. As he sent it around, it seemed to be kind of sluggish. He thought maybe it was going to go too slow, but I told him, that new bearings come with some kind of grease on them, and once you roll them a few times, they really get fast, or put some lubricant on them, and it did. This was his finished cart. We won't go over the details of the cart. That's covered in other documentation I made and YouTube videos. But the front end has degrees of freedom, a little different from the back end degrees of freedom. And he did a great job. This is his propeller in the front. If I was going to do something like this, I'd probably want that propeller to spin better. And so I'd make it out of plastic truss board or thin plywood, so maybe while it was going around it would spin in the wind. We went up and inspected this, and I learned some lessons here from looking at it. I had told him to make sure all of his cameras were on and his GoPro was pointed at his kid's face when he did it the first time, because the boy's only going to ride it the first time, one time, and you want to get that reaction. And he did, and you want to go to his YouTube channel. I'll put a link in the description. And his son really had a great time on this little roller coaster. He did a really good job. So one thing I did notice, that this angle to me, even though we know it's safe because he put 100 pounds on it, ran around a lot of times and nothing bent, so it's safe for his small son. But if I was going to do this, there was a couple things I noted that I would probably modify a little bit, and so I did some analysis for him. I'm not sure if he modified it or not, but it was good like it was. It was just a matter of, well, maybe this is a little better. I thought this angle here looked a little light, and even though it was adequate. And I went home and did some analysis in Fusion 360. Has a finite element package. And so what I did was I said, well, what if we put some braces on the side, welded some braces on the side of that angle, how much better would it get? And the stresses go way down. Now this steel that we use for this stuff is about 36,000 psi strength, and so anything under that that's a yield strength, and so 12,000 it still works fine, but maybe it'd be a little stiffer, and if a larger kid got it, maybe it would be good enough for that too. Engineers always like to have margin in their back pocket. So if you weld it on some braces on the side of that, the stresses go way down. Also, I thought maybe larger bolts would be good. The best thing you can do for a bolted connection is get a bigger bolt and get a higher grade. The grade 8s are significantly better than grade 5. But the best thing you can do is increase the diameter of a bolt. The diameter, the tension strength increases with the area, so with the radius squared. The bending strength is a function of radius to the 4th power, so you can really get a lot stronger as you go to larger bolts. Don't skimp on bolts, especially in a critical place. Get the grade 8s and make them as large as you can within reason. They are more expensive. This is my analysis of I thought he could weld in sleeves. I always, when I put a highly stressed joint together, I'll weld in a sleeve, and that really improves things a lot better too. So you can see we go from the design that was adequate of 20,000 psi there, and if we put the welded brace, welded sides on it and welded sleeves in it and go to a bigger fastener, the maximum stress is predicted to go down under 4,000 psi. So that's 5 times less stress for just doing these details. The crossbar as well, I thought looked a little light, and open holes just aren't that great. If you can weld in sleeves, I know it's a little bit of a pain to weld in the sleeve, but they are so much stronger because the bending stresses in the bar can bypass the hole through those big welded sleeves, and you don't have a stress concentration there. So almost 17,000 psi around that hole with a 100-pound download versus a lot less stress down here, only 2,300 psi if you weld in sleeves and make the crossbar a little deeper. And I won't go through that, but I did learned a great lesson here. What I should have done when I went up to inspect his roller coaster, let me start from the front. I'd said that upstop wheels weren't totally necessary for little roller coasters like this because they never engage. Wheels would never engage if the negative G's weren't high enough. But I take that back. I think we always need upstop wheels, and this is one reason. When he put these bars on, he angled them a little more than 90 degrees, and everything was fine when his son was running it. But I think when a heavier child ran it, the cart tilted a little more, and one of these upstop bars collided with one of the ties and made a noise, and it startled the kid. Nothing was unsafe. It kept going and everything, but I think an upstop wheel would have certainly prevented that, and it's probably a good idea to always put 1 or 2 upstop wheels on every truck assembly. So I learned that. The other thing I should have done when I was up there is grab the cart and push it to the left, tilt it to the left, and run it all the way around the track, and then grab the cart and push it to the right, tilt it to the right, and push it all the way around the tracks to make sure that nothing on the cart would interfere with anything on the track, any framing or anything on the track, and that's a good thing to do. So I learned a lesson there. Like I said, he had his GoPro and all the cameras on, and you can see that at this link on YouTube. I'll put a link in the description. But he got a great video. He spliced it together, and like I did with one video, licensed it through Jukin Video in Los Angeles. They give you 70% of what they make on it, and they sell it to lots of different places, and it's turned out really well. He's got over 41 million views, and that's going to pay for a significant part of his son's college or something someday. So it's really cool. And they were featured on several local and national television shows, like my coasters have been. Scott's a great guy. He had a great father, and he did a great job. He did all the work. I didn't build anything. I just did some design and analysis for him and outlined the testing you should do to make sure it's safe. And they had a great time doing it. And I encourage you to go to his YouTube channel and take a look at that. I've helped a lot of other people with backyard coasters, done some analysis for them and things like that. Got them in the ballpark for whether it's going to work or not and how well it'll work and stuff like that. And it's been a fun thing. So thanks for watching.